In this lesson, we are going to start by reviewing the intervals of increasing, decreasing, and constant for a function. Just remember that a function is considered to be increasing when it's going up from left to right. So for example, if we look at our graph to the right-hand side, we can see that the function will be increasing from the first point that we have on the left, which would be a -5, up through about a -4. So increasing functions are always going to be going up from left to right. As a function is decreasing when it's going to be going down from left to right. So in this case, we can see that starting at -4, the function's going down, and it's stopping at about -2. So that would be an interval where the function is decreasing. So decreasing when the function goes down. A function is constant when it is flat, or essentially it's a horizontal line. In the graph that we have to the right, we actually have no intervals where the function is constant. It's either increasing or it's decreasing. So with that in mind, then, we want to use this graph and we want to find the actual intervals of increasing, decreasing, and constant. So again, the intervals of increasing will be going up from left to right, decreasing going down from left to right, and then constant would be a horizontal or flat line. So our first interval of increase, as we saw before, would be starting at x equals -5 and going up to x equals -4. Now, a few quick notes. When we're writing our intervals of increase and decrease, we want to make sure to always use our x's. So as I was talking, is that for our interval of increase, we'd be starting at x equals -5. And then it would be ending at x equals -4. When we're dealing with intervals, we're talking about interval notation. And the other important note is that when we're talking about intervals of increase, decrease, and constant, we always need to use an open interval, which means that we need to use parentheses. A function is not increasing or decreasing or constant at an endpoint or where the function is changing direction. So from -5 to -4, the function is increasing and we would be using parentheses. So that would be our first interval where the function is increasing. So we want to look where else the function is increasing. So I'd say it's probably starting at x equals -2 and going up to, so although that's at a 4, realize that is at x equals 0. So we're not going from -2 to 4, we're going to be going from -2 to 0. Because remember, again, we're talking about that x value. And then I think we have one more interval of increase, which would be from x equals 2 to x equals 4. And those would be our intervals of increase for the function f of x that we're given. So same idea, we now want to look at our intervals of decreasing. Continuing to look only at our x's, and we always want to use parentheses. We can see that our function is decreasing from x equals -4 to x equals -2. So using parentheses, -4, -2. Let's see where else we're decreasing. So we're decreasing, I would say, from x equals 0 to x equals 2. And then we are decreasing again one more time from x equals 4 to x equals 5. And again, just make sure that we're using the parentheses with that open interval. Finally, we want to look at our intervals of constant. As I mentioned when we were reviewing what our intervals of constant meant, it would mean that if we had any flat lines or horizontal lines in our actual function, since we don't have any, we can just say that there are no intervals of constant. In the first example, I mentioned that we need to use an open interval or parentheses when we're talking about our intervals of increase, decrease, and constant. And that's because at the endpoints and at anywhere where the direction changes, there is no, the function is not increasing, decreasing, or constant. So then the question becomes, what do we call those points where the function changes direction? And we actually call those points relative or local extrema. So as we can see up top, relative, local extrema. So that would be where the function changes direction. So what's important to understand about this is that we're only looking at where the function either goes from increasing to decreasing or from decreasing to increasing. We don't have any local extrema when we're dealing with constants. So there's no local extrema if we're going from increasing to constant, from constant to increasing. There's no local extrema if we're going from decreasing to constant or from constant to decreasing. Our first relative extrema is called a relative or local maximum. Our relative or local maximums occur when the function goes from increasing to decreasing. Essentially, you want to think of this as the top of a hill. That seems to be the most helpful way that students are able to visualize it. So if we look back at where our function is increasing and decreasing, one example would be that's increasing from -5 to -4, and then it's decreasing from -4 to -2. So that point where we change directions from increasing to decreasing would be considered a relative maximum. So for this part, one relative maximum would be at -4, 4 as an ordered pair. So again, a relative maximum occurs when the function goes from increasing to decreasing. It goes up and then comes down. Again, you want to think of it as the top of the hill. Now, there can be multiple relative maximums. So, as we just said, is that one relative maximum is the ordered pair -4, 4. Now, this is also where it can get confusing because here, this is an ordered pair, not interval notation. So -4, 4 is the actual point right here on the graph would be considered a relative maximum. Let's see if we have any other relative maximums, because like I said, there can be more than one. So if we look again, where is the function going from increasing to decreasing? We're coming back up from -2 to 4, sorry, -2 to 0, and then we're going back down from 0 to 2. So we can say at this point right here, we would have a relative maximum, and that would be the point 0, 4. And then we have one more relative maximum, again, where we're increasing and then decreasing, so we're going up and coming back down. That would be at this point here, which would be the point 4, 4. So again, these are ordered pairs. We have 3 relative maximums. So as you might have guessed, a relative or local minimum occurs when the function is decreasing and then increasing. Looking at our graph, we're going from decreasing to increasing. From about, starting on the left, from -4, we're decreasing down to -2, and then from -2, we're increasing over to 0. So our relative or local minimum would be at that ordered pair, which some people like to think of as a valley. So you have your hills would be your maximum, your valley would be your minimum, would be your relative minimum would be at -2, -4, again, because we're talking about ordered pairs. Again, if we look at anywhere else that we're decreasing and then increasing, we're decreasing from about 0 to 2, and then increasing from 2 to 4. So we can say that 2, -4 would be another relative minimum. Now, when they're asking for a relative minimum, sometimes it'll say find the function value or find the value. That means that it only wants the y coordinate where the function has a relative or a local maximum or minimum. So for example, if it asks for the relative maximum value, we would be talking about just the y coordinates for each of your ordered pairs. So it would have a relative maximum value at y equals 4. So 4, 4, and 4. We would have a relative minimum value at -4 and -4. Just make sure that you read the directions to see the format that it wants the answers. And again, how I wrote it here shows them as ordered pairs, not interval notation. The interval notation is what we use for our increasing, decreasing, and constant functions. Next, I just want to talk about odd and even functions. Professor Messenger did provide an overview in the video, so hopefully you got a chance to look at it. But we also can say that a function f is even if f of negative x equals f of x, which should also say is that even functions are symmetric about the y-axis. So for example, if we think of our x squared function, that looks more like f of x equals x squared plus 1. That would be symmetric about your y-axis, so it's an even function. A function is odd if we can show that f of negative x equals negative f of x. Odd functions are symmetric about the origin. So, for example, if we have the x to the third function, that would be an odd function. So in the video, Professor Messenger did show how with polynomials we can examine the exponents to show if a function is odd, even, or neither. But it's also important to know how to do it algebraically, which is showing using this function notation of f of negative x. Also, because if we don't have a polynomial, this would be pretty much our only way to illustrate, other than graphing it, that the function is odd or even. So something like the absolute value of x would be hard to show if it's odd or even, since there are no exponents in it. So now we want to show if the function f of x equals x to the third minus x squared plus 4 is odd, even, or neither algebraically. So algebraically means showing that f of negative x equals f of x for it's even, or f of negative x equals negative f of x if it's odd. So first, we want to evaluate f of negative x. So we would have f of negative x, just substituting in negative x into the functions. We have negative x to the third minus negative x squared plus 4. So this is where it's important to understand how we evaluate x to the negative third and x to the negative 2. So first, kind of as a side note over here, if we have negative x to an even exponent, it's going to be the same thing as if we just evaluated x to the even exponent. So think of negative 3 squared, right? 2 is even, so it'll be an even exponent. That would be negative 3 times negative 3, which would be a positive 9. Well, that answer would be the same thing as if we just did 3 squared. If I did 3 squared, that would be 3 times 3, which equals 9. So we can say that negative 3 squared is equal to 3 squared, or more generally, negative x to the second power would equal the same thing as if we took the positive x to the second power. And even really more generally, saying that negative x to an even power is just going to equal x to an even power. Looking at our odd power, if we have negative x to an odd power, that's going to equal negative on the outside x to that same odd power. So for example, if I did, let's do negative 2 to the third. So negative 2 to the third would be negative 2 times negative 2 times negative 2. Well, negative 2 times negative 2 is positive 4. 4 times negative 2 is going to be negative 8. If I just did positive 2 to the third would be 2 times 2 times 2, which would be positive 8. Now, these are not equal like we had with the even exponent. But what our answer does equal is if I did negative 2 to the third. If I did negative 2 to the third, that means you would do negative 2 times 2 times 2, which would give you a negative 8. So, again, we can generalize this by saying negative 2 to the third in parentheses is the same thing as taking the negative out. So that way here we can just say that negative x to the odd exponent is equal to negative on the outside x to the odd exponent. So this is an important concept that's going to come back, so you want to make sure that you do understand it. So let's use those ideas to evaluate the two exponents that we have in our f of x, f of negative x. So negative x to the third, 3 is an odd exponent, so negative x to the third means that we're going to be taking out the negative and rewriting this as negative x to the third. So the exponent still stays and the negative comes to the outside. Alright, so this becomes that whole piece. Next we want to do negative x squared. Well, since negative x is being raised to an even exponent, that means that we're just going to rewrite this part as x squared. the negative on the inside goes away, but the subtraction on the outside comes down. And then we're left with plus 4. So we have that f of negative x is equal to negative x to the third minus x squared plus 4. If we can show that f of negative x is equal to f of x, then the function would be even. If we look at our problem, we have negative x to the third minus x squared plus 4. Going back to the original is x to the third minus x squared plus 4. So that first term is not the same. So that means that it is not even. So not even. Nope. Not even, since they're not equal to each other. If they're not even, then we need to continue working through the problem. If we show that it's even, then we're done. So then second, we would need to evaluate negative f of x, which really mean negative the quantity of f of x. So when we distribute the negative into the original f of x function, we're left with negative x to the third plus x squared plus 4. To show if the function is odd, we would need to show that f of negative x that we found in the first part would equal negative f of x. Well, we want to compare then our two answers. So looking at what we have f of negative x is equal to negative x to the third minus x squared plus 4, and negative f of x is equal to negative x to the third plus x squared minus 4. So as we can see is that we have an issue first with our second terms because those are different signs, and then we also have an issue with our last terms because those are different signs as well. So that means that the function is not odd. So that means that the function is neither. And going back to what Professor Messenger said in the video, is that since this is a polynomial, we have exponents that have different, that are both odd and even. So x to the third, 3 is odd, 2 is even, and then 4 is x to the 0, and 0 is even. Since we have a mixture of odd and even exponents, that also will prove to us that the function is neither odd nor even. So just one last example tying in why we need to understand how to do the f of negative x part. Is that if we want to figure out if the absolute value of x is odd, even, or neither, if we first just look at what the graph is of absolute value of x, the absolute value of x is really just a v. And by that graph, we can see that it is symmetric about the y-axis. And when it's symmetric about the y-axis, that means the function is even. Well, let's try to see why that is. So going back to what we did before is that our first step is that we need to find f of negative x. So if we do f of negative x equals the absolute value of negative x, the question is, what does that equal? Well, what happens when we take the absolute value of a negative number? For example, if I do the absolute value of negative 2, that really turns the number positive to give us a positive 2. Another way that I can get a positive 2 answer is if I just did the absolute value of 2. If I just do the absolute value of 2, that also gives me 2. So we can then generalize this, and so it will always work out that way, to say that the absolute value of negative x, the absolute value of a negative number, would be the same thing as if we just took the absolute value of that number. So f of negative x, when we plug it in, would be equal the absolute value of negative x, which would then be the absolute value of x, if we're simplifying it completely. At this point, then, we would say, okay, well, if it's even, then f of negative x should equal f of x. Looking at what we have f of negative x equals the absolute value of x. Well, the original function was f of x equals the absolute value of x. Since they are equal, then we can say that the function is even, which means, as we saw from the graph, it is symmetric about the y-axis.